Good morning. It's August 28th, and this is your daily brief in science. Here's everything you need to know. A new After-School Alliance report shows a clear rise in after-school STEM learning, with 92% of parents reporting these programs offer STEM opportunities, up from 69% in 2014. That growth signals a stronger emphasis on science, technology, engineering, and math in after-school care. Yet access gaps remain, as more than 3 in 4 parents who want such programs still cannot enroll their children, especially outside urban areas. Nationwide, roughly 23 million children lack access to an after-school STEM curriculum, underscoring a broad reach of this access challenge beyond New Jersey. Jody Grant, Executive Director of the After-School Alliance, cautions that gaps persist and calls for expanded funding from local, state, and federal levels plus philanthropy to close them. Ebony Grace, CEO of New Jersey's After-School and Out-of-School Time Professional Network, notes benefits like exploring interests, solving real-world problems, and building teamwork and academic skills. Experts highlight mentorship as essential for sustaining girls' participation in STEM, with role models and support particularly influential in aerospace and related fields. In Prince George's County, Maryland, hands-on microbiology projects using microscopes sparked curiosity by letting students observe microorganisms. Accessibility challenges hit low-income and rural families hardest due to cost and availability. The study is supported by the Overdeck Family Foundation, with the After-School Alliance advocating universal access to high-quality after-school STEM through ongoing research and policy work. Programs cover robotics, math leagues, and other activities for elementary through high school students, prioritizing hands-on, collaborative learning without grading pressure. The report lays out policy recommendations to expand access and quality, boost funding, treat after-school as a STEM education partner, invest in CS, tech and engineering and professional development, expand rural and virtual programming, foster real-world partnerships for older youth, link STEM to durable skills, and target summer funding to high-demand areas. A low-temperature path for graphene growth is challenging the traditional high-temperature barrier in CVD. Researchers use acetylene on CEO2 to grow graphene-based materials at temperatures as low as 300 degrees Celsius instead of the usual 900 degrees Celsius, aiming for energy efficiency and better structural control. The work appears in the Journal of the American Chemical Society, June 2026, with authors Mengshuan Zhang, Takaharu Yoshi, Qi Zhao, Yuichiro Hayasaka, Davis Di Tommaso, and Hirotomo Nishihara. A joint team from Tohoku University and Queen Mary University of London demonstrates graphene growth at 300 degrees Celsius on CEO2 surfaces, enabled by acetylene. They report that low-temperature synthesis reduces growth temperature, potentially enabling energy-efficient production and better material control. The study frames this approach as a blueprint for low-energy, eco-friendly carbon manufacturing with recycling and upgrading of low-grade carbon resources. Professor Nishihara emphasizes the method's potential to convert waste gases, biomass, and recycled plastics into high-value carbon materials. The paper highlights the possibility of integrating this method into recycling-oriented carbon manufacturing and scalable applications for practical use. Low-temperature CVD offers improved structural control by bypassing the rapid, high-temperature growth that traditionally complicates graphene formation. The authors note that the process overcomes rapid, high-temperature growth, delivering controllable graphene-based material structures. Cerium oxide creates oxygen vacancies that facilitate acetylene decomposition. At 300 degrees Celsius, acetylene extracts oxygen to form additional vacancies that act as active sites for graphene growth. A new study from OIST and partner institutes shows that complex sugar chains called glycans on gangliosides and many membrane proteins frequently form brief homodimers in the plasma membrane, influencing membrane organization and signaling. Using single-molecule imaging, researchers observed CIS interactions between glycans on the same cell, creating membrane nanodomains that modulate signaling pathways. The work demonstrates that repeated short-lived glycan encounters can influence EGFR activation and cell division, offering a mechanism to regulate growth factor signaling beyond ligand-induced dimerization. A central finding centers on GM3 ganglioside, which suppresses EGFR dimerization only when it forms homodimers, with the paired glycans binding to corresponding EGFR glycans to renew a brake on EGFR activity when stimulation is absent. GM3 gangliosides were observed forming relatively long-lived homodimers that assemble into rafts associating with EGFR, where GM3 glycan interactions dampen EGFR dimerization and activation. The study shows that GM3 acts as a temporary brake on signaling only when organized as GM3 homodimers, curbing EGFR activity in the absence of external cues. The researchers suggest that similar glycan interactions could regulate other receptors, potentially broadening therapeutic strategies beyond protein and lipid-centered targets. Fleeting glycan-glycan encounters help couple gangliosides, drive membrane nanodomain formation with cholesterol, and regulate EGFR signaling, a key pathway for controlling cell division. Overall, these very short, repeated glycan-glycan interactions can produce stable regulatory effects on receptor signaling and membrane nanodomain dynamics over longer timescales. The findings hint at new cancer biology and therapeutic possibilities, proposing that transient glycan pairings, when repeated, shape receptor signaling and membrane architecture over time. A new approach combines a patent-pending Petri dish method with a computer model of about 150 heart signaling nodes and thousands of variables to test drugs in silico for fibrosis progression and treatment responses. The model aims to identify biomarkers, predict how patients will respond to therapies, and narrow down drug candidates by simulating heart biology and running multiple treatment scenarios. Funded by the NIH's National Heart, Lung, and Blood Institute, the project maps signaling pathways and tissue responses in systolic heart failure to uncover drug targets and new therapies. A key objective is validating findings by comparing patient-derived samples with experimental results to speed translation from model to clinic. Researchers seek to map how individual heart cells respond to mechanical stimulation and to identify biomarkers that indicate treatment efficacy and disease progression. Tissue and blood samples from patients with left ventricular assist devices will be used in Fayetteville to grow cells and study collagen accumulation, fibrosis development, and changes in electrical signaling. Collaborations with Dr. Michael Zeil and Dr. Amy Bradshaw at MUSC will provide damaged heart tissue to support the study of fibrosis and tissue responses. The effort emphasizes personalized medicine, tailoring potential therapies to patient-derived cells and samples to guide pharmaceutical development. The computational model will identify biomarkers predictive of fibrosis, forecast treatment responses, and potentially reveal drug targets to slow heart damage while guiding virtual drug testing and combination screening. By enabling virtual testing and target discovery, the model aims to spur pharmaceutical interest in new therapies for systolic heart failure and fibrosis. University of Arkansas Associate Professor Will Richardson will lead a 4-year, $2.16 million NIH-funded study to investigate systolic heart failure and its underlying fibrosis, with goals of developing personalized treatments. The grant supports exploring causes of systolic heart failure, identifying potential medications, and leveraging patient-derived data to tailor therapies. A new all-optical platform is mapping metabolism and cell identity in intact tissues at subcellular, single-cell resolution, redefining how we see immune and tumor biology. REDCat combines Raman-based metabolic imaging with high-plex protein markers, autofluorescence, and tissue morphology to link metabolic state with precise cell identity on the same tissue section. Background work shows its utility in normal lymph nodes, where distinct metabolic programs exist across immune cell types and spatial niches, and in lymphoma, where lipid and redox remodeling emerge and intratumoral heterogeneity is exposed. The workflow profiles fresh frozen or FFPE tissue to extract label-free features like NADH, Fad-redox ratios, and lipid states, then integrates roughly 50 protein markers via codecs with HE and aligning images and segmenting cells to join identity with metabolism through MaxFuse for joint embeddings. Spatial analysis reveals intact compartmentalization in healthy nodes, but disrupted neighborhoods in lymphoma, signaling altered microenvironments and potential immune metabolic consequences. In longitudinal tumor studies, REDCat identifies 8 lipid-rich SRS clusters in tumor regions and links spectral clusters to codex identities, uncovering metabolic heterogeneity and possible transition states during CLL to DLBCL transformation. In Richter S transformation, widespread metabolic reprogramming is seen with tumor clusters showing higher lipids and NADH-FAD ratios, along with architectural disruption and subclusters echoing CLL and DLBCL-like states. The platform integrates Raman imaging, autofluorescence, and high-plex immunofluorescence to capture metabolic features across tissues and demonstrates cell type-specific metabolic programs in healthy nodes, such as varying redox and lipid patterns in germinal center B cells and other immune cells. Overall, REDCat delivers submicron, multi-omic mapping of metabolism linked to cell identity, enabling insights into immune physiology and tumor metabolism with potential therapeutic implications for lymphoma and beyond. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. We'll be back Monday with everything you need to know.